In this video, we're going to practice using the VR Shear tool and compare it to the DMD output. If you have this loaded from the previous exercise, then you can just sit by while we just review this in case someone new has started it. If you don't have this display, then all we did was went to a WFO scale and 120 frames, and we loaded a KCRI all tilts base data, and we loaded the algorithm overlay DMD. The other thing we did was we went into the Tools menu and we loaded the radar display controls. Alright, so when we have all this loaded, what we're going to do to use the VR Shear, before we do this, we want to get our DMD a little bit more visible. So we're just going to change the minimum feature strength to a 5 on the DMD. Our store motion, doesn't matter what we put in here. When we're doing rotational velocity calculations, it's independent of reference frame, so you could be using base velocity, SRM, any motion you want, and your velocity differences will not change with any of the changes in store motions. So it really doesn't matter about the store motions. That's just for making things look more symmetric. So we'll go ahead and toggle over to reflectivity using the dot key on the keypad, and we're going to zoom in to the storm northeast of the radar. It has these two DMD detections over here. And we are going to step backward to 2329. Alright, we toggle over to velocity. We can see, let's go ahead and step through this loop forward a little bit. We see that there's a circulation in there. It's kind of noisy and jumps around a bit. We're going to stop at 2329, 0.5 degree SRM. Now we're going to want to go ahead and zoom in to the SRM display on the upper left, hitting the 1 key on the keyboard. And we can hit the dot key on the keypad to toggle over to SRM. So for now, let's go ahead and just toggle off the DMD overlay, and under the Tools menu, we're going to load VR Shear. Now there's a trick to setting the anchor points for VR Shear. We can see we have a mesocyclone in here with outbound velocities. The radar's down here on this side and inbounds on the other side. So we've got cyclonic shear on this side, and we also have some anticyclonic shear on this side of the updraft. So for this cyclonic mesocyclone, we can, after we've loaded the VR Shear, we're just going to right click on one endpoint on that peak velocity, and we're going to right click on the peak inbound velocity. That's a quick and easy way to set our anchor points for VR Shear. Now we're also going to go right click on VR Shear legend, and let's go ahead and change the color to yellow so that we can see this better. So the VR Shear is calculating rotational velocity, so that's the outbound velocity minus the inbound velocity divided by 2. And it's also giving us the distance between these 2 points, 2.4 nautical miles. It's giving us the shear, which is the rotational velocity divided by the diameter. And then it also gives us the distance from the radar. So we see a 35 knot rotational velocity at 90 nautical miles. We can bring in our mesocyclone diameter sheets from some of our training in the radar and applications course to kind of put this in some perspective. We have a diameter of 2.4 nautical miles, which is kind of in between these two. So let's start off on the top one. If we go 90 nautical miles, 93, and about 35 knot rotational velocities, we're in the moderate rotation category. If we were to have something that was a smaller mesocyclone diameter, which is slightly smaller, if it was as small as 1 nautical mile, then we see at 90 nautical miles, 35 knot rotational velocities would be strong rotation. So it's somewhere between moderate to strong. It's fairly long range detection. We can get some sense for where we are in the storm. If we want to load the pop-up skew T, go into the volume menu and click pop-up skew T. Then we'll right click on the background, and under the sample cloud heights, we'll change this to wrap. So if we go ahead and sample out this display, then I'll bring this into my cave here. All right, if we sample our display, we see that we are way up in mid-levels in the storm. We're at 12,000 feet above sea level, 10,000, 10 to 11,000 feet above ground level. So we see with the dot on the sound display that we're way up at the kind of the start of the LFC, and most of the tornado genesis and the important mesocyclone dynamics are all happening in the lower levels, and we're nowhere near that. So this is a storm at far ranges where we have lots of uncertainty in trying to do mid-level rotation using that as a forecast parameter for tornadoes. So that just gives us a little bit of perspective on what our mesocyclone height is at this range. So if we're issuing a tornado warning, then this is really not a high confidence prediction. Moderate to strong rotation at long range. If the environment's very favorable, then perhaps, but we don't have the typical hook echoes and other things that we can see at closer ranges. So this is kind of a fairly common signature at long range, high false alarm rate, but at least we can get a sense for the rotational velocity that we are in the moderate to strong category, and we do need to watch this carefully. If I wanted to go ahead and just do a manual calculation, I'm just going to grab this and left mouse click on it and hold and drag that out of the way. I'm going to go ahead and sample these and make my own calculation on my head, because once you get used to doing this, it can be sometimes faster to do in the VR Shear tool. 37 knot outbound velocity is the peak I see in there. 37, and I got a 31 over here, so 37 minus 31 is 68. 68 divided by 2 is 34, so I get a 34 knot rotational velocity, which if we put our anchor points back on there, I think we've got 34.5, so it's all consistent. That's another way of doing this. And it's important to point out now that let's compare this to DMD and see what it came up with. We can look and we see we're on the extra sails tilt, and the DMD is actually at 2327, and we are a couple minutes from when that base of that DMD was being calculated. So I'm going to go ahead and I'm going to step backward one tilt to go to 2327 on the SRM product. Now it's going to match the 2327 with the DMD. Let's do another calculation here. Repetition is always a good thing. I see the peak outbound velocities right in here. Peak inbound velocity, I'm going to first look at the pattern across a given range. We don't want to be choosing velocities that are way out here, 45-degree angles. You want your angle to be within 30 degrees to do these shear calculations. Otherwise, you're really not able to factor in the kind of convergent and divergent rotation signatures. So we're just going to be doing the more straightforward azimuthal shear calculations here, kind of at fairly similar ranges. So I'm going to sample these out. We've got 22 there and a 22 there, so it doesn't really matter. Either one is fine to choose. So we get a 35.5 knot rotational velocity, which is about 36 knots. So that's very similar to the extra sails tilt this time. We got some noisy velocities up here and something kind of weird happening up in different parts of the storm. But we're going to be kind of looking at this area, and let's go ahead and compare this to the DMD. So we've got 2327 SRM and 2327 DMD. And the algorithm came up with a number of different attributes. We see the R7 in the DMD sampling indicates we're going to left mouse click and hold on the DMD circle to identify the sampling readout. R7 stands for a 3D strength rank of 7, which, if we remember that the 5 was kind of the base definition of mesocyclone, 7 was in that moderate category. It can be moderate to strong depending on range, and this is fairly far range, so it's getting into the more strong than moderate. The next knot velocity in there, 28.8, is actually the gate-to-gate velocity difference, which usually 90 knots is fairly strong, but 28.8 is weak, and we can see that there's not any strong gate-to-gate velocity differences in this part of the mesocyclone. There's some funky things going on in here, but that looks very noisy, and I don't know if I trust that data very much. If we go to the next number in there, the 38.5 knot is the maximum rotational velocity that the DMD detected for this area is 38.5 knots. So really not too much stronger than what we've been sampling. Nothing significantly stronger than what we've been sampling at 0.5. So let's go ahead and tilt up from 2327 using the up arrow. We'll go to the 0.9 degree tilt, and we can do another calculation here. We just move our anchor points here over to peak inbound, peak outbound, peak inbound velocity, and we get 36 knot rotational velocities there. Keep tilting up. We see now at 1.3 degrees, if we were to try to do this again, you can say, oh, look at this velocity in here. This peak inbound is 43.7 knot inbound velocity, and that cranks our rotational velocity up to 47.7 knots. Now, the reason why I don't do this is because if you look at the continuity, it's just not there for to support this as being a trustworthy inbound velocity on a mesocyclone. Whenever I do rotational velocity calculations, I want to see some sort of horizontal, vertical continuity as well as temporal continuity to the signatures that I'm analyzing. And if I tilt downward, I see that there's a lot of continuity. I'm going to tilt back up 0.9, 1.3. There's really no vertical continuity with that. I go up a little bit higher, and now I see it still doesn't have the continuity that it has kind of down low. So this velocity looks a little suspicious. Let's go backward in time one by hitting the left arrow, and we see that there's really not a lot of continuity for this velocity. So I am not going to use that as my rotational velocity. Instead, I'm going to go out to a velocity that's kind of at similar ranges within 30 degrees of kind of that range and that perpendicular to the beam there, and I get 36.5 knot rotational velocity. So you can kind of see the general approach for doing rotational velocities. You can do this manually. You can just move this stuff out of the way, and I can just sample this and go, okay, what's the maximum outbounds? 51.5. I'm going to go maximum inbound is 20.4, so it's 51.5 minus 20.5 is 72. Then 72 divided by 2 is 36 knot rotational velocity, and that matches roughly what the VR shear tool is coming up with. So you can do manual calculations of rotational velocity in your head, or you can use the VR shear tool. And if you're going to use VR shear, then remember that you can always do your anchor points by just right-clicking on one peak velocity and right-clicking on the next spot. That's a handy little trick to using VR shear. The other elements in here are we have the, let me reset this. We have the rotational velocity. Let's go ahead and move this back onto the peak. Rotational velocity, diameter between the peaks that we've done, and the shear. And remember, rotational velocity is going to be a lot more stable parameter than shear. You need a lot of sampling observations before you can use shear, because if you have just a couple of radar range gates, let's say 3, that are sampling a mesocyclone, that beam is so large at these long ranges that it could be off by 1 gate or 2 gates in position. And if you factor that in, that's going to fundamentally change your diameter, and when you divide by it, it's going to fundamentally change your answer. And if it's a really noisy field, which we typically get when we only have a few samples, then your shear is going to be jumping all over the place. So unless you have a very well-defined, well-sampled mesocyclone with lots of observations, like 6 or so, then it's really not a good place to start for beginning radar interpreters to use shear. We strongly recommend from WDTD to really use more rotational velocity, and just remember that the general rotation, once you get up around 30 knots, that's a significant rotation that's starting to form, and then once you get up to 40, that's that moderate, and 50 is strong rotational velocities, and that can be critical in doing tornado warning forecasts where you're looking for strong rotation on radar. It's close to the ground, which in this case we don't have, and then using that with the environment to make a warning decision. So that's it for VR shear.